according to Sebastian, this is a Pokemon guy. Is that right? I don't know anything about Pokemon. I do understand this. And I understand that this guy is an approximation. The less segmented and the smoother out we can make that approximation, the better. Okay? And that's exactly what we do when we go from taking a Riemann sum, which is a summation of pieces, and we go to an integral, which would actually, so the Riemann sum is going to be those rectangles, adding up all of the rectangles of different size, right? We did like this, versus the sum, or the integral, just computes the area, and it's smooth, and it's beautiful, and it's no longer an approximation. Okay, but while we kind of anticipate that, and we know we're going in that direction, especially having been there already in physics, we're going to take some breaths in the calculus and figure out what we're doing. All right. This is taken directly out of your textbook. This is, if you were following along in your book, page 400. Okay, you don't have to look at it, but I do want to show you. We've got different options for Riemann sums and different options for how they can be computed. One is called a left Riemann sum, where we take all of the left sides of the rectangles. Okay, so let's say that I'm looking at a picture. Okay, we've got some kind of function here. And I want to know, where do the left sides of my rectangles hit that function? So I'm interested in only this side. Depending on the concavity of the function, we know that a left-hand Riemann sum is an overestimate, right? If it's concave down, it's an overestimate. If it's concave up, then my left-hand sum is an underestimate. Can you see that? Okay. But depending on whether I'm talking about a right or a left-hand Riemann sum will determine which side of the rectangle I want to use. Right? We looked at, when we were doing our limit notation, we had this f of x sub k business times delta x. Well, f of x sub k tells me how high is my rectangle based on the function. Are you with me? If I'm talking about a left-hand Riemann sum, then I'm talking about the left corner height of the rectangle. Can you see that? If I'm talking about a right-hand Riemann sum, given the same function, I could be talking about the right side of this rectangle. Which is different. If it's concave down, my right hand is an underestimate. Can you see the difference? So it matters. It matters, am I doing a left Riemann sum or am I doing a right Riemann sum? Am I using the left side of the rectangle to find f of x? Or am I using the right side of the rectangle to find f of x? Which one's more accurate? And if I want an overestimate, if I'm trying to figure out how much paint it's going to take, then I probably want an overestimate. I want to have a little bit smidge more paint than I need, right? If I'm trying to find out how much money it's going to cost, I'm hoping maybe for an underestimate. I don't know. I mean, that's a bad situation. But you understand that, like, it would matter, okay? And they're different. What could be more accurate? Okay, if I find the height of the midpoint. So if I take the right side and the left side, and maybe I just split them right down the middle, and I find the height of that value. That's a midpoint sum. So I'm going to go back to this page out of the textbook. The midpoint of each subinterval is found by doing half of the left and the right. In other words, they average the left side and the right side, and that puts them right square in the middle. Are you with me on that? Okay, this is called a midpoint sum, noted by x bar. This is x with a bar on top. That's how you know you're dealing with midpoint. X bar means average. It's kind of more of a statistics thing. Okay, so what they do there is they take the left x value, the height, and the right x value. Okay, and they split, not the height, the x value and the right value, and they split them, and then they find f of the dead center value. Okay, so if I was looking at 1 to 2, I would go to 1.5, and I would find the height of that value on the function. Okay, it's the middle. Cool? The other option here is called a trapezoidal sum. Trapezoidal sum takes the height of the right and the left, and it splits that. So instead of going in the middle of the two values and finding that height, it's finding the right height and the left height, and it's averaging those. A lot of times you'll see that the trapezoidal sum is more accurate, because instead of operating this rectangle here or here, it's splitting the difference. It's catching both. Okay. Again, this could be considered to be the left side of the triangle, where this would be the right side of the triangle. So if I was operating on the rectangle, if I was operating on a left Riemann sum, I'm way under. If I'm operating on a right Riemann sum, I'm quite a bit over. A trapezoidal sum splits the difference. It's a little bit underneath, it feels, but it's a lot closer than either one of the other options. Okay, so how does that look in a formula? So instead of taking half of the difference in x values to find the middle, it takes half of the difference in the heights. You see? It's an average of the two heights, versus on the midpoint, it was an average of the change in x values. Midpoint puts you in the middle between your two x's. Trapezoidal takes the middle of the f values. This is why I'm not in the textbook. Look at this picture. Y'all see this? The green is a right Riemann sum. The blue is a left Riemann sum for the same x interval. Note the difference in the two. Do y'all see that difference? Right would be way over. Left would be way under. The trapezoidal sum is able to say, let's take the average of the differences. Where would the midpoint sum fit on this picture? What would I do for the midpoint sum? Yeah, see, y'all been sleeping. In between. So we would take this xi minus xi sub whatever and split it. And we would find the value of the function here. And then I would deal with that rectangle. Okay, a little bit more accurate. Not quite as accurate as the trapezoidal. Okay? Okay, let's get out of the book. Get out of the weeds. One thing that you do need to know is how to write them down. Okay? You're going to be tested on your AP test. In the free response portion, you're going to get points for writing it down correctly. More points there than you get for actually computing with the right numbers. They want to know that you can process. Okay? So while we start working in your circuit, we're going to practice, how do I come up with this? The rule. You understand? Okay. So this is one of my favorite circuits. This is written by Virge Cornelius. And I don't want to work all of it because that would be spoilers and providing things on YouTube that I'm not supposed to provide. But I will work a couple of them with you. You don't have one? You remember I gave you one on Friday?
I think I left it in my car.
Cooper, Charles, Clarence, Cooper the third. Yeah.
Like, actually?
Well, it's disrespectful. I mean, she's gone through a lot of time to not put out a solution. So I'm just going to work a couple.
Just state that.
Yeah, disclaimer. I am not providing solutions to Virge's wonderful circuits. I'm going to work a couple.
I'm going to send it to her and be like,
Okay. All right, so number one right here. It says, during a time interval from 0 to 8 minutes, water drains from a large vat at a rate of g of t gallons per minute. The function g of t is a continuous function. Select values are indicated in the table. Use a left Riemann sum. So you want to underline the word left. because that's going to tell you which side of the rectangle we're interested in. Okay? With 4 subintervals of equal width, that's important as well, equal width, to approximate the amount of water in gallons that drains from the vat over the time interval. Okay, so here's what we're going to do. We're going to draw a picture. The picture will absolutely save your bacon. Okay?
You're saying only 4 rectangles?
Right.
Oh.
4 rectangles. So 4 subintervals of equal width. Now my table's got 89 values, but I'm not going to need all of them. This is where the picture comes in handy. Okay? So draw yourself from 0 to 8, maybe a number line. And I don't know. We need 4 subintervals. We can use the fact that it goes from 0 to 8. That's our b minus a. So b minus a over n. That always tells me delta x. Tells me the change in x. If they are equal width, then delta x is the same for every rectangle. Okay? In this case, b minus a is going to be 8 minus 0 over n number of rectangles. How many? 4. So in this case, the change in rectangle is going to be 2, which means starting at 0, I'm going to hop out then to 2. And then next will be 4, and then next will be 6. How many rectangles do I have now? 1, 2, 3. See, we did it.
Nice.
We said it. Okay, so now how tall are my rectangles? How tall are my rectangles? So I want the left side of these 4 rectangles. So from 0, I'm going to hop up to g of 0, which is 2. So this is going to go up 2 spaces. And this is going to be my rectangle for my first partition. Sorry. Now, how tall is my second rectangle going to be? 3. Because I'm reading f of 2, g of 2. G of 2 is going to be 3 high. The left corner is going to go up to 3. Are you with me? How high is g of 4? 4. So this one's going to be 4 high. How high is g of 6? Read it. 0. So there's no rectangle there. Do I need g of 8? What's g of 8 going to give me? It's going to give me the next rectangle, which is over here. Do I need that? No. It's not on my interval. Can you see why I didn't draw it? Okay. So what we're going to do, if we are using a left Riemann sum, is we're going to add up these rectangles and their height. Okay. So the formula that we're going to use here is to say delta x times the height of each individual piece. Now, if delta x is the same every time, then we can factor that out. But we know what we're doing is we're adding up the area of each rectangle. So that delta x is on the bottom. That would be 2 times 2. Area would be 4. 2 times 3. Area would be 6. 2 times 4. Area is 8. And we're going to group them all together, right? But if that is equal partitions, equal sized, then you don't have to do the 2 times every time. And you can factor out that delta x. So really you have delta x times all of the y values. F of, which one did we get first? F of 0 plus f of 2 plus f of 4 plus f of 6. This is where you get so much credit on these AP questions. They want to see that you can write out the Riemann sum. Okay. Now, what is delta x? In this case, that delta x is 2. So I have 2 times, what's f of 0? 2. Plus 3 plus, okay, 2 plus 3 plus 4, 9. 2 times 9 is 18. There's our approximate value, 18. Okay. And again, that came from delta x times f of 0 plus delta x times f of 2. And you're doing length times width, length times width, length times width. But if that delta x, the width, is the same every time, factor that dude out, and you don't have to deal with it over and over and over. Are y'all with me? Okay, so that takes us, 18 is the answer here. So that takes us to number 2, which I believe is on the next page. What do you think? Okay so far? Okay. It says during the time interval from 0 to 8 minutes. Okay, so again, B minus A is going to be 8. Water drains from a large vat at a rate of G of T gallons per minute. Function G of T is continuous function. So as far as we can tell so far, this is the same as the first one. But now it says use 8 right-hand rectangles. 8 right-hand rectangles. Okay, so we're going to draw our picture of equal width, which means that delta x number is going to be consistent. It's going to be the same every time. So we're going to draw our picture. We are on an interval from 0 to 8. If I take 8 minus 0 over 8, what is my delta x? 1. So that means I get to jump out to 1, and then 2, and then 3, and then 4, 5, 6, 7, and 8. Y'all with me? Now, we're going to draw our picture, but we're based on the right side of the rectangle. So do I want to know what is f of 0? My picture is going to determine based on what is f of 1, which is what? 3. So I'm going to go up to 3 and over to 0. There's my rectangle. You see why I don't want 0? It's a right side, so I jump to the right. What's my next thing that I want to know? What's f of 2, which is also 3? What's f of 3? Okay, that's going to be a little taller. What's f of 4? F of 5? Itty bitty guy. F of 6? 0. F of 7? 2. F of 8? Now I am interested in f of 8 because I'm on the right side. So the right side of my rectangle determines its height. Okay. So now to compute, we're going to have delta x times f of 1 plus f of 2 plus f of 3 plus f of 4, f of 5, bless you, f of 6, f of 7, f of 8. And you see why it's helpful to be able to factor out that delta x? Because I don't want to type that. Delta x times this, delta x times this, delta x, length times width, length times width. I don't want to do that. Y'all with me on that? Delta x also in this case is 1. So that's super dandy. What was f of 1? So 3 plus 5 plus 4 plus 1 plus 0 plus 2 plus 5. 14, 16, 17, 18, 19. Nope, I missed one. 15, 16, 17, 18, and 5 is 23. Okay, So that was, the first one was an example of a left side where we bumped everything to the left and we read those values. On the right side, you bump everything to the right. So you're not going to use the first one, but you are going to use the last one. You with me? Are we really understanding this? Okay. Let's go to number 3. This time we're doing trapezoidal. Okay, it says during the interval from 0 to 8, water drains, blah, blah, blah. The function g of t is a continuous function. Select values selected in the table. Use two trapezoids of equal width to approximate the amount of water in gallon drains from the vat. Okay, only two. So in order to compute delta x, we're going to have 8 minus 0 over 2, which is 4. So that means on my interval from 0 to 8, I'm splitting it. And I want to know what's happening from 0 to 4, from 4 to 8. That leaves me 2 partitions. Delta x is 4. How do I compute the trapezoidal? Well, the trapezoidal takes the average of the left and the right value. The average of the left and the right value. So in the beginning, you're going to have a half delta x. There's the average. That half splits it. Okay? This rectangle is going to have height at 0 and height at 4. For this particular rectangle that would appear right here. So we're going to have half times delta x times f of 0 plus f of 4. And what that does is that gives me the height on the left side and the right side. And the half takes the average. You with me? Now let's bump to the next rectangle. Plus what? So we still have the half delta x. I factored that out into the front. But what are the two sides of this second rectangle? F of 4 and f of 8. Good. So you see that 4 feels like it's repeating. Well, it's because it's the right side of the first rectangle, but it is the left side of the second rectangle. So when you're averaging those sides, that's going to count twice. Any questions on that? Okay. And our delta x in this case was 4. And f of 0 is 2 plus 4 plus 4 again plus 5. Okay, at this point, I'm going to stop recording. I feel like that's probably a pretty good idea. No. I want to work one more with you before I stop it. Yes. Okay, so go to page 98 on the bottom. It says page 98 on the bottom. And it's going to be the top one on page 98. Answer 16. This is not number 16. I'm not going to tell you what number it is. I just want to work this one with you. This says compute a midpoint Riemann sum. Midpoint Riemann sum. Okay. To approximate the integral from 1 to 4 of f of x dx with given these values in the table, use 3 partitions of equal width. So now what's your b minus a? 4 minus 1. So delta x is going to be b minus a over n. In this case, 4 minus 1 over 3. 3 over 3 is 1. So delta x here is going to be 1. Now, how do I do midpoint? So draw your picture first. We're going from 1 to 4, and we want to split it into 3 partitions, each partition being 1 apiece. So what's next after 1? 2. Good. And then 3. Now, I'm not interested in the values 1, 2, 3, or 4. Look, we do have 3 partitions. We did it. Yay. I'm not interested in those values. I'm interested in the midpoint between those values. You see how the midpoint comes into play? So I don't want to know what is f of 1 or what is f of 2. I want to know what is f of 1 plus 2 divided by 2. 1 half, 1.5, right? So that puts me in this position here, and here, and here. Those are your midpoints. So how tall is it when x is 1.5? 7. That's the rectangle I want to know. How tall is it when x is 2.5? 1. How tall is it when x is 3.5? That's what we're interested in. So not the left side, not the right side, the middle. Okay. 3 partitions. Good question. So the actual write out of this is going to be delta x times f of 1.5 plus f of 2.5 plus f of 3.5. And I'm kind of hesitant to already jump to this step. What I feel like initially would have been this ideal delta x times f of 1 plus f of 2 over 2. You know what I'm saying? No, wait. Not f of 1 plus 2 over 2. Like this. Hold on. F of 1 plus 2 over 2. That x value is what's getting averaged, not the heights. That would be on trapezoidal. Plus f of 2 plus 3 over 2. Plus f of 3 plus 4 over 2. That's how we're coming up with these numbers. 3.5, 2.5, 1.5. Is that making sense? So then when we actually compute, delta x is 1. F of that 1.5 we said was 7. F of 2.5 is 1. F of 3.5 is 12. I got 20. Okay. And again, I don't know what number that is, but I just thought you should have access to that example as well. Okay? So carry on, finish the circuit. We'll start the next section tomorrow.